Tubbenhauer, who will give us a primer on finitary two representation theory.
Yeah, thank you very much. And of course, I would like to thank the organizers, all of which are here. Well, no, Anton is not here, but anyway. So I would like to thank the organizers for organizing this lovely event. I really enjoyed this 1.5 weeks so far. And, well, I hope that at least some nice, papers will come out of the lots of discussions I had with several people here. So yes, so my topic today is joint work with those guys, Marco, Walter, Vanessa, and Joey. And I'm going to talk about something that I really fell in love with in the last, 1.5 years, which we call finitary two representation theory. So the idea for today is to basically give you some feeling what this finitary two representation theory is all about, because I'm really not assuming that you're an expert. I know that there are some experts in the audience, but I don't speak to you, okay? I'm keeping it very low, and, well, my long-term goal somehow is to turn this finitary two representation theory, which still is a slightly abstract and very technical language in some sense, very powerful in my opinion, into something combinatorially. And I will show you today how far I got. In particular, if you were here, let's say last week for Sergei's talk, he usually likes to talk about this back of the envelope calculations. It isn't as easy for me. I can't do back of the envelope computations, but I can do computations in using some computer algebra systems, for instance. So there's a lot of combinatorics going on, and that's what I'm trying to explain. Before I'm getting started, there are 3 main examples I want to keep you in mind of things I want to study. So my main idea, which I'm going to explain in some philosophy session in the first, let's say, 15 minutes, is that I'm not really interested anymore in studying an algebra and its representations, or an algebra and the fixed representations, but rather I want to pick a fixed category and study something like its true category of representations. And some of the main examples, of course, if you ask such a question, which is basically asking, can you categorify representation theory itself? It's a very hopeless question, of course. So you need to restrict kind of the categories you want to study acting, and also the categories you act on. And that's what's hidden in this word finitary, which I'm going to explain in the talk. But the main examples which I would like you to, which I really would like you to keep in mind are those 3. And I hope at least one of them is something you like. So first of all, something group-like a category of vector space, G-graded vector spaces. That's a very easy. So all of these will be monoidal categories. So that's a very easy monoidal category where your objects are just the group elements. There are no non-trivial Hom spaces, and the tensor product is just mimicking the group multiplication. It's a really naive categorification of a group, if you want. And in this theory, it will turn out that this guy will have very, very nice associated 2 modules, which I'm going to explain in a second what those 2 modules are. And actually, they are so nice that I'm going to do it live. So I basically classify 2 modules for vec G in my talk. That's something I hope everyone can understand. Some finite group, some category, which basically is still the finite group. And you're asking for functors where the finite group, categories where the finite group can act on. Another category which I've turned up quite a lot this week are those fusion categories. So take some SLN, GLN, whatever. Take a root of unity, so the quantum version, and semi-simplify. Those are usually also very nice categories, and in contrast to people like Katharina, who is not here anymore, or David, I'm not really interested in the modules in this category, but rather, let me stress this again, in the categories where this category acts on, which is kind of a higher level, if you want. And those 2 have in common that they fit into something which is called usually fusion categories, which is kind of the semi-simple world. And the third example, which doesn't quite fit into the semi-simple world, are Zergel bimodules or Hecke categories, so categorification of Hectare algebras, which are not semi-simple, and we also want to study kind of two representations of those guys. And the main theorem, which I hope will not be a failure, but which I have in mind, and I hope there will be a paper on the archive at the end of the year, being completely aware that the year just started, is that we can finally classify the two representations of this category. And the main trick, from which I will explain two ingredients, namely the two combinatorial ingredients, will be to reduce this case, the non-semi-simple case, in some way to the semi-simple case. Okay? And even if you have never seen this before, I think you can all, well, it's not very hard to guess that the semi-simple case is supposed to be much easier than the non-semi-simple case. But let's see how far I will get. The main ingredients will be cells. So I'm going to explain very combinatorial, some generalization of the Castellustic cell theory. There will be a very nice trick which is called the H Cell Theorem, which I'm going to explain in the last, well, let's say 10 minutes. And the only missing ingredient, which I can't explain, but I'm just mentioning it here once, is called the asymptotic limit. So this category actually has an associated asymptotic limit. If you think in terms of Hectare algebras, it's like something taking your quantum parameter to infinity. And this asymptotic limit has some very nice properties. In particular, it fits into here. Okay? So the main theorem basically states that this guy, the two representations of this guy, are parametrized by the asymptotic limit, which actually fits into here, and here you basically know what to do. So that's the main theorem, which hopefully will appear, as I said, before next year, or maybe before my next visit to the ESE. Okay, so let's get started. This is a rough outline. I'm going to do some philosophy in the first 10 minutes to get you started, because it's early morning, right? And I will stay most of the time in the decategorified story, really explaining the combinatorics, something you usually don't find in those written in those papers, which are, I admit, not very easy to read. And at the very end, I explain a little bit about the categorified picture. That's my rough outline. And whenever there are questions, just feel free to stop me, of course. It will be very combinatorial. I hope you will like it, because I like it very much. Okay, so as I already said, so this is my main question. Okay, I want to categorify this picture. Take a finite-dimensional algebra. Well, I think everyone here would agree that studying its representations, so actions on some endomorphism space of some finite-dimensional vector space, that's something reasonable, right? You associate to each algebra element a matrix, right? And what you usually do in this setup is you have some notion of atoms. We will see this on the categorified level as well. Let's say for me the atoms are the simples. I like simples. And the nice fact about simples is that everything has Jordan-Hölder filtration, so everything is filtered by simples. So in some sense, those are the atoms of your theory, and you should study those atoms. Why is this interesting? Let me click on this funny link here, just to get you started, because it's one of my favorite quotes. So the whole theory goes back to people like Frobenius or Burnside, which was a very long time ago, okay? And when they started this theory, it was absolutely not clear. So Frobenius started it basically because he liked matrices, and it was absolutely not clear to other people why it should be interesting. In particular, Burnside himself said when he was studying this very famous book, Theory of Groups of Finite Order by Burnside. The first edition is, as I said, very old, and he basically says what Frobenius did is useless. He says it would be difficult to find a result that could be mostly directly obtained by the consideration of groups of linear transformations. So groups of linear transformations is his name for representations. So he basically says representation theory is useless. Okay? That's basically what he says, right at the first page of his book. A few years later, he completely changed his mind, and is now one of the fathers of representation theory, and he writes, in fact, it is now more true to say that for further advantages in the abstract theory, one must look largely to the representations of a group as a group of linear substitutions. So he says, we completely turned his mind, right? From 0 to 1, just completely turned around. And this is part of why I really want to push this two representation theory further. maybe from the viewpoint from today, it's not really clear whether it's useful, or so we don't have real applications outside of the field itself. But maybe it's roughly like this story. When Frobenius started it, he really just loved matrices. He just did what he did, calculated with characters quite a lot, as you will see on the next page. So this is from Frobenius' book. So the first ever published character table. This is the one. So he basically already knows everything. So characters are indexed by, so that's what he writes here in the text. Characters are indexed by conjugacy classes, simple characters, and he calculates the first character table for the for A4 in modern language. So for the symmetry group of the tetrahedra. So 12 elements, A4. So he just did it because he liked it. And then it turned out to be super useful, and I think nobody nowadays would doubt that representation theory of groups is something very useful and very nice. And I hope actually the same will turn out to be true for this true representation theory, which I'm going to explain. Please keep in mind that there is a root of unity, or please note that there is a root of unity, which turns up here. In this case, it's a third root of unity, but there is a root of unity, and this will matter in my story. So just keep in mind that there is a root of unity. Okay, so this is basically philosophy. I want to categorize this picture, right? So the main goal would be to classify simples, and I want to categorize this picture. That's basically what we want to do. Okay, so let me explain one of my main players, namely the Hectare category, without mentioning what the Hectare category actually is. So what we usually, and one of my main examples here will be the easiest example of a Coxeter group, which is a dihedral group, which is just given by a generator relation presentation as above. So we just write out two generators, call them S and T, and they are reflections, so they should square to 1. And they should satisfy a braid relation, which I will explain in a second. Namely, whenever you have n factors of alternating symbols, you can just turn it around. Okay, so very easy question, and actually those are the symmetry groups of the what is it? The n-gon in the plane, and this is how it works. An idea which goes back to Coxeter. So what you do is you fix a flag, and the flag is, oh, I'm explaining this such that you can generalize this to higher dimensions, so keep track. So you fix a flag, and the flag is nothing else, in this case, than a point and a line. There's one. And you fix a hyperplane permuting the 0 cells of the flag. You fix a hyperplane permuting the 1 cells of the flag, and those hyperplanes will be the hyperplanes corresponding to reflections in those generators, and you just keep going. So you write down a vertex for each hyperplane which you have written, and you connect them by an edge corresponding to the angle. And this number tells you the length of the braid relation, which you then can easily check by just reflecting in those hyperplanes. Here's the example. If you want to write down the Coxeter complex, you just take those hyperplanes and you reflect, and you get the whole dihedral group in this case, which is of order 8. Those are the elements of the dihedral group. And this is all very nice, and they have associated Hectare algebras, and so forth and so forth. And the ones I'm interested in to consider this question are the so-called finite Coxeter groups. Here's a list of diagrams, and they correspond in a very similar way. I've just shown it to you for the dihedral group. They correspond to symmetry groups of certain regular polyhedron. The families you should keep in mind. So those are, by the way, the Weil groups up to G. So A up to G are the Weil groups, and then there are some exceptional groups and the dihedral groups. And the way to keep them in mind is, for instance, that H3 correspond to the symmetries of the regular dodecahedron, or dually the isocahedron. And it turns out that those polytopes only make sense in a certain dimension. So you can see the list of different Coxeter diagrams of finite type. So all of these will give finite groups. You will see in a second why I want finite groups. And you see in dimension 1, of course, it's a bit boring. In dimension 2, you have the dihedral groups. It's the only case where you have infinitely many. And afterwards, you have some exceptions. In dimension 4, you have quite a few. And then it stabilizes. So if you ever ask where have you seen this sequence before, it's a sequence of dimensions of the corresponding finite multiset groups. And it turns out that those are really, really, really nice groups, and they have an associated Hectare algebra, which I will come back in a second. But this is kind of my main example, which I want to keep you in mind, where you can feed in here basically any symmetry group of some regular polyhedron thingy. Okay. And now I want to classify for you in one slide. On one slide, I want to classify for you the simple representations of the dihedral group. You basically can ignore the one-dimensional ones. If you think about this relation, and you want to have one-dimensional representation, and you just say, well, you can send those two guys to some element, and because of this order, because of this relation, you get independence, whether it's even or odd. But in the end, you end up only with 2 or 4 of them, and they're just given by specifying whether you send S or T to 1 or minus 1, okay? The two-dimensional representations are a little bit more interesting. The two-dimensional representations are given by those matrices, which are basically given by the rotation action of the dihedral group on the corresponding polyhedron. And they are given by specifying a certain very strange number here, which we don't like from the viewpoint of categorification. You will see later why or how it turns up, by specifying a certain cosine number, which is actually really basically the angle between the two hyperplanes. And the proposition, which I don't know in this formulation, this is certainly known to Lustig, but I mean it's representation theory of the dihedral group, so this is ancient. The proposition is then, this is a complete list of simple representations. So only 1 and 2-dimensional ones. So this is what I want to stress. Only 1 and 2-dimensional ones, but their number grows because, well, here you see the dependence on n, right? The more n you have, the more of those angles you will see, and the number of 2-dimensional ones will grow. Okay. However, you see those funny numbers, complex parameters, and in particular, this doesn't work over the integers, right? And this will be crucial because, well, decategorifications of modules should be something integral. We will see it in a second. But keep it in mind, representation theory of the dihedral group is very nice. It's basically, ignore the one-dimensional ones, it's basically given by specifying the angle. This is what I want to do, and this is what I'm going to explain in the very last, let's say, 15 minutes or so. So instead of considering now a group acting on a vector space, I want to consider a certain category with finiteness conditions. Well, the slogan is finitary means whenever you see something that could be finite, it is finite. So whenever you ask yourself during my talk, is this group finite? It is. Is this vector space finite? It is, and so forth. Everything that could be finite is finite, roughly. Later I will give you the formal definition. And I really want to study something like this, right? The categories, but not really the objects or morphisms or whatever, but their actions on other categories. And then the collection of all those two representations, that's what we call a two representation. So instead of basically, morally speaking, instead of associating to an algebra element a matrix, I want to associate to an algebra element a functor, right? Keep in mind that I'm always having this integral stuff going on, right? Because if you decategorify a functor, you only see integers, or actually positive integers. We will see this in a second again. But the point is, the whole story seems to repeat. Okay? Later I will show you the formal definition of what a two-simple is, but there is a definition of an atom, the categorification of a simple module, if you want. I just call it two-simple. And they satisfy very similar properties, like all two modules can be built out of two simples. So there's some kind of a Jordan-Hölder filtration theorem. It's not as completely nice as it is. It's called a weak Jordan-Hölder, but it's something you don't have to care about for today. Okay? The point is, it's a very, very similar story. So the real goal is to classify those two simples. So basically the categories which you can cook up such that you can act with your favorite category by functors on this category. In some sense, you want to classify functors, which 10 years ago I think was kind of a hopeless problem, but nowadays we can actually do quite a lot, which is very, very impressive, I think. So these are my main examples I want to keep you in mind. Same as here. So example of vector space, so this vec G, the naive categorification of a group, or alternatively, if you want, rep G, complex representations of a group, which are very easy, and I will really discuss the classification of two simples in real time if you want. It's not really hard. The other examples which we have seen. Yes?
Do you consider a monoidal structure for C?
For C, yes. In this case, oh yeah, good point. In this case, C is a monoidal category, all of them. For vector, yes, the trivial one. So no twisting. It's really the most naive categorification you can cook up. No twisting. Yes, so let me stress that all of these are very easy examples of monoidal of two categories. They are monoidal categories, so two categories with one object. But the theory applies in more generality. So classification here is easy. For those, they're still semi-simple. You can still do something like there are only finitely many two simples, which you can't do here in the non-semi-simple case. But the classification is a bit more complicated. I won't go into too much details. I'm doing SL2 for you. If you ask me later, I can do SL3, SL4, and so forth. But it's not complete. So this is roughly speaking trivial. This is not trivial. It's already interesting, but not too hard. And this is really hard because it's non-semi-simple. In general, we have absolutely no clue how those two representations are supposed to look like. And hopefully the main theorem will actually tell us what they are. But that's work in progress. By the end of the year, maybe. God knows. And in this case, really, classification is known basically only in two special cases, which I'm going to discuss during my talk. So that's so much about philosophy. Any questions? Very good.
For you, finite means finite-dimensional.
If you see finite, everything that could be finite is finite. Finite-dimensional vector spaces, finite-dimensional Hom spaces, finite groups, finite number of objects, finite. Okay? I will come back to this later with a formal definition. But everything that that could be finite is finite. Okay? But the reason is very easy. Already on the decategorified level, having a satisfactory theory of infinite dimensional algebras is, well, finite dimensional stuff is just much easier. Okay. Oh yeah, I wanted to show you the dihedral case. So what you do is, there's a Kastalustic basis, and you fix this basis. You will see the difference in a second. And what you want to cook up a two representation is basically a category where you can act on, and the functors for your fixed basis, and the relations of the functors. The relations of the KL basis of your fixed basis have to be satisfied by those functors. And there's a coherence condition, which basically boils down to that I should take the two category, which I'm not going to explain. So if you know what circle bimodules are, then this would be a functorial action of circle bimodules. But I'm not going to explain circle bimodules. Not because it's really hard, but I think either you have already seen them, or it's useless to do it in 2 seconds. But this is what you should keep in mind. You fix the basis, and you want functors for your basis element satisfying the relations of your basis element. And it turns out that this is a classification in this case. So circle bimodules stated otherwise. Circle bimodules for the dihedral case, for the dihedral group, I have two simples indexed by ADE Dünken diagrams. Okay, so the non-trivial ones. There are two trivial ones which we don't care about, and the non-trivial ones are indexed by ADE Dünken diagrams, depending on. So n was, as I said, n was the number of edges in your regular polyhedron, so dn. So let's say for n equals 6, you would have 1, 2, 3, 4 associated two simples. They correspond in 1-to-1 correspondence to those Dünken diagrams. And it's actually not so hard to cook up the corresponding categories if you know zigzag algebras, and you take the zigzag algebra for the corresponding quiver, take its modules of its category of projective modules, and that's where you act on. But for now, this is enough. And this is quite nice. And surprisingly, those guys have turned up in Sergey's talk on Monday, and I really wonder about a connection. But so this would be maybe the first application ever of this whole theory. So I was really surprised on Monday. But I can't say anything more. The point is, those guys, and I can explain it later if you ask me, are really related to those fusion categories. So in some sense, the dihedral group is a non-semi-simple version of the fusion categories, and they're connected by something that's called the quantum Satake, which I'm not going to explain. But it's basically the same story, and it turns out that this classification, which is already very hard for the dihedral group, the way you do it is you reduce it to this case where you hit representation of SL2. And for representations of SL2, you can do something. You get an ADE classification, you pull it back, you get an ADE classification here. That's the main idea underlying my theorem, which I hope there will be an archive paper at the end of the year. Notice here one thing. In contrast to the simples, they don't grow in number, but they grow in rank. So the size of the module can be read off by just the number of the nodes. So this is the rank. So this is rank 5. And ignore the exceptions, then at one point this will just stabilize and you either have 4 of them or you just have 1 of them. But they grow in rank instead of growing in dimension as the simples do. So it's completely different, and you will see in a second why. Okay. Okay. So now comes the algebraic setup. And this is what I want to think about. So now really some definitions and properties. So I want to fix an algebra, okay? Yeah, for sure. But I want to fix the basis of the algebra, and I'm demanding that the basis has positive structure constants, okay? Think about, I've already chosen a category, and now some indecomposable objects in my category will categorify down to such a basis. But I'm only explaining the decategorified picture. So fix the basis with positive structure constants. Well, here it's trivial. Here it's just a group element basis. We will see it in a second. Here, for instance, it would be this tilting basis Katharina explained on Tuesday. And here it would be, for instance, a KL basis you could fix. But it really depends on this choice of the fixed basis. And similarly for a module, you call a module a positive module if you want, if all your fixed basis element acts by non-negative integers on the fixed basis. You can also say all your fixed basis element act by non-negative matrices, right? Matrices with non-negative entries. And of course, the pseudo example is, of course, these are these decategorifications of my two representations upstairs, right? If I decategorify a functor, I don't see negative numbers. But here comes a real example. If you take the group algebra of just any group and you fix the usual elements of the group basis, then the regular module is an example of such a positive module. That's, I hope, quite clear. And now comes the point. The regular module usually over C decomposes into simple modules. But this decomposition here, I've sneaked it in somewhere, equivalence in this setup means there is a base change matrix with only positive integers, right? You want to realize everything on the categorical level. So your base change matrix is only allowed to have positive integers. In particular, usually you can't use the usual decomposition, which you know for simples of groups, because you will do some Jordan theorem, which involves complex roots, like we've seen before. So usually the regular module in this setup is not decomposable into the simples. It's almost never the case, actually. I will come back to this in a second. Another example is, of course, this one. So Hectare Algebras, in contrast to the upstairs one, let's say for the symmetric group, you can either fix the KL basis or you can fix the group element basis. You get completely different answers, okay? It's very important that everything depends on the fixed choice of basis. It took me a very long time to learn this because I somehow entered this field of categorification by categorification of quantum groups, where there's this kind of a God-given basis. But in the end, in all this categorification stuff, downstairs, it really depends on the choice of basis, which is basically saying you choose your categorifying category. And here's a really nice example where you get a completely different answer, which I'll show you in a second. So either for the symmetric group, you can choose the KL basis, or for any finite Boxer group, you can choose the KL basis or the group element basis. You get completely different answers. For the symmetric group, it's actually quite nice. Some miracle happens, namely all the simples are already integral over the KL basis. So if you write down the character table, in this case of S3, all of you know you have 3 simples. You write down the character table, you see some negative numbers in the usual group basis, but if you write it in the KL basis, all negative numbers vanish by a miracle. They just disappear. Everything is positive. This is really, really cute, and this is true for all symmetric groups. I just did it in this example, and of course I was lazy, so I fit it into the computer. But you could have done it by hand. So everything just vanishes, right? So some negative signs, woof, they are gone. And it's very easy to compute. So this guy, for instance, is just the sum of all of them. And if you just take the sum of all of them, you get, of course, 6. That's how you calculate those numbers. And all of them will be positive. So this is really nice. So the simples in this case are already defined integrally. That's also how you can phrase it. Oops. For the hidden group, as I already showed you, it's wrong. So this is horribly wrong in general. It's a nice feature of the symmetric group. And in some sense, the reason why type A sometimes is so much easier than other types. So type A, by the way, again, was the symmetric group. Okay. And now, now I want to study this integral representation theory, which again, let me stress it again, is a decategorification, the shadow of a two representation theory upstairs. And the key fact to keep with you from this slide is that there's a very nice way to study them. And it depends on the cell theory, which hasn't appeared. So let me explain. So whenever you fixed a basis, like I did, you can talk about cells. And I will give you more examples in a second. You just say, 2 of my fixed basis elements, let's say are left lower. X is left lower than Y. If, let me think about my notation. If you can find another basis element, call it Z, which you can multiply to X, and of course you can decompose this into some sum over basis elements, right? And if here Y appears, then Y is bigger. I hope this is my convention. Yes. So so X is lower than Y whenever you can, from the left, whenever you can find another basis element such that you multiply them in the decomposition, you will see the other one turning up. In particular, 1 is always, so the unit is always the lowest, because of course 1 is lower than X is just saying you multiply X, right? So X turns up in its own decomposition. In particular, 1 is always the lowest element in this order. So this gives you a pre-order, which is not very hard to check. Similarly, of course, from the right and from the two-sided. And the equivalence classes you can form using this order, they are called cells. And they are the Kastalustig cells in some sense, in the case of the Hectare algebra. So you order your things by using cells. And you call a module transitive if it's basically one equivalence class. You can do the same for modules and so forth. And you call a module transitive if it is one equivalence class of a cell. That's when you call it transitive. And the transitive ones are, in some sense, the building blocks of the theory. So they are the simples of the theory. And the nice fact, which I will show you an example in a second, is that each transitive has a unique apex, which is a unique maximal cell not annihilating your module. So the cells, so this gives you rise of decomposition of your basis into certain cells. You will see some examples in a second, whatever. Okay, this gives you a partitioning, and actually this also gives you an ordering of those guys. So you get an ordering on the cells. And for each such module, there will be a unique maximal cell not annihilating it. everything below will annihilate it. So you can order your representation theory by cells, by putting them into cells by saying, okay, I'm only studying a certain fixed apex now. I will give you an example in a second. I will skip this due to time reasons. But transitive ones are the simples, which just means they are one connected component under this equivalence class. Okay, let's do one example. Let's do it live. For group algebras, okay? Okay, what happens for group algebras if you fix a group basis? I told you already that 1 is always in the minimal cell, okay? But if you have now an inverse, this is saying in my notation that 1 is left bigger than, what is it? G inverse in this case. And of course you can do it the other way around. In particular, as soon as you have inverses, everything will cluster in one cell, namely in the cell of the identity, which in this case is the group itself. So those guys have a very, very easy cell theory. And those guys, by the way, as well, as you can check for yourself, if you think I have now some, so those fusion guys usually have some dual elements, and as soon as you have a dual element and you're in the semi-simple case, if you write an equation like this, you're already done, you're already ending up in the cell of the identity, and everything will cluster in one cell, which is a big difference between those two pictures. So in the semi-simple case, all the cells will be just one big cell, and here we will have a really rich cell theory. Okay. And the transitive modules, you can actually check quite easily now what could be the transitive modules. They're exactly given by specifying those, specifying a subgroup and by letting your group element act on the conjugacy classes. And this gives you the complete description of the transitive modules in this situation. And the apex, of course, of this guy is G itself, because there is only one apex and everything is invertible anyway. And this is kind of the whole drawback, or if you want, of the theory. As soon as you have something invertible acting, and you think about, I want some element should act by an invertible functor, or on the decategorified level, by a matrix with only non-negative entries. Whatever, something like this. If you think about it for a second, there are not too many matrices which are invertible with only non-negative entries, which are invertible over, which are invertible in this sense, in this positive sense. They are only permutation matrices, and that's why you end up with this classification here. So it's very easy. The Hectare algebras, let me just show you how the cells look like. In type A, they are very nice. They're given by the Robertson set correspondence. If you've never seen this before, but it doesn't matter so much. But you really have cells now. You can calculate left cells, you would have 4 of them. You can calculate right cells, you would have 4 of them. And two-sided cells, you would have 3 of them. And in this case, we would have 3 two-sided cells in my notation: green, purple, and orange. And this was the table from before, and you can really see the apex here, right? The biggest cell not annihilating it is green, right? So the sign module is here. The biggest cell not annihilating it is orange. The biggest cell not annihilating it is this one, which is the corresponding apex of the corresponding simple. Remember that the simples are exactly I haven't said it. The simples are exactly the transitive modules in this case, because they are already defined integrally, as I said before. Okay. Yeah, so another example, if you take G equals Z mod 3Z, and we find exactly 3 conjugacy classes, we have 3 associated simple modules. Let me just click on the link. You all know how it works, right? Takes the regular representation, do Jordan decomposition. You will see those matrices turning up. Here are the roots of unities. That's exactly the ones that specify your simple modules. But we can't do this integrally because, for instance, over F3, you do Jordan decomposition over F3, and you realize, oops, the regular module is indecomposable. In particular, you can't do this decomposition over the integers. And it turns out that's exactly the reason why the transitive modules in this case are given by subgroups. And how many subgroups of Z mod 3 do you see? I see 2. Both of them are trivial. So you only have a one-dimensional and a three-dimensional associated transitive module in this case. This is really the difference between the classical theory and the decategorified shadow of the categorified theory. Right, so that's what I write. Let me do another example, just to be sure that we are all on the same page. Coming back to my dihedral group, okay? I told you that the choice of basis is extremely crucial, and here you can see it. So in the dihedral group, let me just do the case of D8, okay? You can write down the list of simples. There you go. You can write down the dimensions. You have a sign, this is a rotation one, this is a trivial one. That's the one you would study in classical representation theory. You use complex numbers, you use Jordan decomposition, you compose your modules, you would see those guys turning up. If you would fix now the group element basis, you would have to look at subgroups of the dihedral group, which is of course not very hard. It's a bit too hard to do it live, so I cheated and I already did it. So those are the subgroups up to conjugacy of the dihedral group. Those are the associated ranks of the transitive modules. As you can see, it gets completely different. And I've just written down, for instance, if you would, so this one is of dimension 4, and if you would decompose it integrally, over the complex numbers, you would see this decomposition. In particular, you can check now by hand that all of those are different if you want, right? So this one cannot be this one, and so forth. But you don't see this, so this clusters together in a 4-dimensional module. Okay? The regular one clusters together in an 8-dimensional module. You cannot split off anything. If you choose a KL basis, you get this funny ADE classification. And you get, again, a completely different result. In this case, your rank sequence is 1, 3, 3, 1. So we have 4 of them, and this is how they look like if you want to decompose them. And you can actually, again, see that those are different. So here's the sign difference. They look very similar, but in the end, there will be some slight difference. So this is really the difference. It really, really depends on the choice of basis, or said for the people who love categorification, it depends on the choice of your categorification. Okay? Okay, everyone happy? Good. So there's one class of modules which I want to promote here, which are called the cell modules. You should think about them as being induced modules. For each, let's say, left cell, right cell, whatever you want, you have an associated cell module by just taking all the elements, right? I've defined my order upstairs. Oh, this one is gone. If you look just at the definition of the Kastalustig cell order, it somehow builds that everything gets bigger in this order, okay? So you can just take some induced module in some sense by saying, okay, from my left cell onwards, I take all elements which are bigger. This gives you a module basically by definition. And then you kill all stuff which is strictly bigger. And that's what you call the cell module. It's very similar to defining a Verma module, for instance, like Pedro would like to do it, who is not paying attention. Anyway, so those are basically the induced modules in this theory. And it's very easy to see that all of these are transitive. Basically, by definition, they are transitive. And the main question somehow is, well, like in those theories, you will cook up a very class of nice modules, standard modules, Verma modules, whatever you want, and you ask yourself the question, do I get everything? Are there some other modules? Are there some other simple modules? That's roughly the same as the question, are there actually transitive modules which are not cell? And everything, again, of course, comes from a categorical picture. So let me discuss this in a second, in a few examples. In my first running example, well, I only have one cell. So formally speaking, most of my modules are not cell modules, but morally speaking, I want to count them as cell modules, right? Because they're kind of cell modules for the smaller group, if you want. So it's not quite true what I've written upstairs. But in this case, it's just so easy. I just want to include it in the case where cell is the same as transitive. Okay. For Hectare algebras of symmetric groups, the cell modules are the transitive modules, are the simple modules. And so those are really casualistic cell modules, if you know this language. Let me check. Yeah, I can click on the example if you want. So this is how it works. So you write down, what I have done here is a computer calculation for the symmetric group. Which one is it? With 24 elements, so it's A4. And those are the cells. You have 5 of them. They are ordered from 0 to 4, very boringly in this case. These are the number of elements in those cells. It's always the same. The bottom one is just the identity. The top one is the longest word. And in the middle, you can see funny stuff turning up. And all you do in this theory is you remember, so this is the cell, this one, the 9 times 9 cell. You write it in terms of left cells, which are my columns, and in terms of right cells, which are my rows. And you just remember the number of elements, because in the end, it doesn't really matter what kind of elements you see here. Just remember the number of them. And it turns out that what you see here is not a coincidence of type A. It's what's called strongly regular. Okay? So in type A, all cells are squares, meaning all those numbers are square numbers, as you can see, and this is the general fact in type A. And all intersections between any left and right cell just contains one element. And 1 is the lowest one, so there will never be 0, so this is the easiest case. So everything just is some big matrix with ones. And it's not so hard to see that in this case, when you only see strongly regular cells, then those two notions are actually the same. So in this case, by the way, you see 3 cell modules, namely, let's say left cell modules corresponding to my 3 rows here, all of which are equivalent, as you can see from the diagram, because they are supported on the same numbers. That's roughly how you check whether they are equivalent. So in this case, you have exactly one equivalence class of cell module, and this is the only one, and that's the corresponding. So this is S4. S4 has 4 simples, remember, just given by partitions, and that's the corresponding partition for the cell. So each cell has a unique associated symbol. That's a simple module you can read off here. Yeah, for the symmetric group, all are strongly regular, but in general, this is horribly false. So this is how it looks like if you do a bigger example, which I just chose to be B6, which has quite a few elements, around 50,000. This is how the cell order looks like. It's quite fancy. You will see really, really huge cells here with 14,000 elements. And they get quite scary. So my notation here just means, well, for instance, 4, 5, 5 in this notation just means it's a 5 by 5 matrix with only 4s. Okay, 5 by 5, okay. So this is a huge, huge cell, and in particular the intersections, as you can see, vary from 4 to 2 to 1, okay? So very complicated in general. Yeah, so this is certainly not strongly regular. And this is why those casualistic theory outside of type A is so much harder than in type A. And most of those numbers are not squares. Whenever you see a square number, it's a strongly regular cell. 900 is a square number, it's a strongly regular cell. And everything is completely combinatorial, you can just do it. Well, if you're lazy, in this case, probably not lazy, you can do it by computer. Okay, this is how those cells look like. In the dihedral case, it's kind of the opposite of the, so the dihedral case is kind of the opposite of the symmetric group case, where you only have 3 cells in general, but the intersections get as big as you want. If you get n letting big, then this will be n over 2, for instance. Again, some parity depending whether it's even or odd. So you only have 3 cells in general. The middle one will be not strongly regular. The middle one will be the one which has the interesting modules turning up, the non-cell modules. In this case, it's type DE Duncan diagrams. Okay. So I have something like 10 minutes to tell you a little bit about the categorified picture, coming back to, oh yeah, so are there questions, of course? A little bit to tell you about the categorified picture. All of what you have seen right up to this point is the decategorification of a bigger story upstairs, and it's really what you never find written in the paper, but that's basically what people do. They sit down and calculate those cluster-lustig cells, or they're lazy and let Sage do it, or any other computer algebra program. But this is a categorified story. There's a lot of text, and I only want you to read the purple one. So I would like to, so in this case now I need to fix my acting categories and where they act on. And what we do is we consider what is called a finitary category. A finitary category is nothing else than you have finitely many isomorphism classes of indecomposable objects, like here, here, or here. So in this case, they correspond exactly to the number of elements of the Weyl group. That's why I have a finite Coxeter group. That's why I have a finite Coxeter group here. And everything is finite dimensional. Like morphism spaces are finite dimensional. Similar on the two categorical level. You only want to have everything finite. Everything that can be finite is finite. You can easily, oh yeah, let me mention this. This is a little bit like with an abelian category. So there's a nice definition of an abelian category, which usually people don't like to write down. And there's a definition of an abelian category that any abelian category is equivalent to R mod for some ring R. Here's an equivalent definition of what's being finitary. Any finitary category is equivalent, this is bad, let me call it C, to A P mod, so projective finite dimensional modules of a finite dimensional algebra. That's also how you can think of it. Right? So finitary categories are exactly a P mod for some finite dimensional algebra.
For several bimodules, do you have a problem with the Hom space?
Sorry, say it again?
For several bimodules, do you have a problem with the Hom spaces being finite dimensional?
Yes, yes. So and for the Zergel bimodules, oh, you're an expert, I see. We take Zergel's version of Zergel bimodules, which uses a covariant algebra, which is finite dimensional in this case, and not the polynomial algebra. But you can make it work for the polynomial algebra. I mean, it's not a huge difference. But that's why you also need finite Weyl groups. It's another reason why you need finite Weyl groups. Yes. And now a simple two representation. So a finitary two category is exactly the same. And you can form a two category of finitary two categories where your objects are finitary two categories. Your morphisms are structure-preserving functors, and your two morphisms are natural transformations. And a two module is just then a two functor from your fixed, one of those guys, from your fixed favorite finitary two category into some nice category where your objects are AP mods. And you basically act by projective functors, which means you choose certain bimodules. Okay? And well, you can also form then, that's what I roughly sketch here. I only have something like 7 minutes left. You can form a two category of two representations where your objects are now those two functors, your morphisms are natural transformations, and your two morphisms are what is called modifications, which is the usual notion you see for three categories turning up. So the next level after natural transformations are called modifications. In particular, you have something like a notion of a two equivalence, and everything is nice. And you call a module simple, too simple, if it has no stable ideals. So you act with your category and you don't find any stable ideal. That's when you call it too simple. And those two simples are exactly the proper notion in this setup of a categorification of a simple module. Okay. Examples, well, that's what I already said. So some facts, and then will come some examples. So you should really think of two simples. So I said again, you fix the category and you act on something with projective functors. And you're looking for some nice categories where you don't have any stable ideals. And those are the two simples, right? You're basically trying to classify projective functors if you want to classify two simple modules. That's why it is so hard for some special cases. So this is basically category O if you want. Yeah, so but the point is also they really correspond to simples upstairs, like you have this Jordan-Hölder's filtration. They don't decategorify to simples. That confused me a lot, that's why I like to stress it. They don't decategorify to simples, they decategorify to the transitive modules. They can't decategorify to simples because simples usually need roots of unities turning up. And you don't see them if you decategorify a function. Right? And you can, I mean, this whole theory, just imagine this whole cell theory, which you just built by just, instead of choosing your fixed basis, just do it for the indecomposable, in this case, one morphisms of your category. Just play the same game, you can define cells, you can define cell modules, you can define transitive, you can define everything. Just exactly the same language. Just replace any plus, that's why we want positive numbers, replace any plus by a direct sum, for instance. And you play the same game, any two simple as an associated apex not killing it, and so forth. You can study everything depending on the apex. So the standard example, which I already did, which is basically the prototypical example of a finitary 2 category. Oh, I've chosen B. B mod, why B? Anyway, B mod for some finite dimension. BP mod for some finite dimensional algebra. Those are really the prototypical objects of this, of my target category, my choice of a vector space. That's my choice of a vector space. So this one, the fairly naive, so no twisting, really the naive categorification is an example of a finitary category. And yes, so now comes something funny which I really want to do. So maybe I have to skip this theorem, but this is really nice because it's something you only see on the categorical level. Okay, I told you that for those guys, the transitive modules, the decategorifications, are indexed by subgroups. I do an example here for you, which is the Klein foregroup. So just the subgroups of the Klein foregroup, you have 1, 2, 3, 4, 5 of them. But on the categorical level, which is connected to Niels' question, you can actually twist your action by a certain element in, which is still a numerical condition, by a certain element in the second cohomology group of the group. And you just check in this case that, for instance, you can twist this representation by a sign on the categorical level, which doesn't work on the decategorical level. In particular, you get two different associated two simples here, which you don't see downstairs. And that's why this categorified theory is so much harder. So downstairs you can see this, upstairs this one splits into two, because there's something non-trivial going on, because you can twist your associators, basically. Something really non-trivial. That's why this case is so much harder. So for instance, to show here that on the decategorified level you get finitely many transitive is not so hard. It's basically a version of Perron-Frobenius theorem. But on the categorified level, you somehow have to control all the possible categorifications of what you see downstairs. And that's just ridiculously hard. Here you are lucky. There's something that's called Ogneano rigidity. Here, in this case, Ogneano rigidity tells you that there are only finitely many categorifications. Right? They are only finite. So even if this gets very funny, this will always stay finite at least. So here you have finiteness, here you don't. Very crucial difference between those two cases. Anyway, you see some patterns on the and this gets, of course, more fancy if you move away from this one to more interesting categories here. Okay. So indexed, it's still a numerical datum, indexed by subgroups and a choice of a twisting of your action. In formal words, a second cohomology group. Okay. Another examples are Tukac-Moody categories. If you make them finite dimensional, like going to Schur quotients. In this case, the categorification, the simples are exactly the simples of Raphael and Kovan of Lauder. Another example is, of course, circle bimodules. The two simples are super complicated, except in the symmetric group case, where the two simples are just the categorification of the simple modules. And you can play funny tricks, like you can take quotients here, certain quotients. Still, everything is widely open. And of course, this case, which fits nicely into this pattern. And yeah, again, for most groups, this is again also this is semi-simple, so you know that there are finitely many. The classification is widely open. Not widely open. You can ask me later. It's not widely open, but it's open. So let me finish with the H Cell Theorem. Yes. Right? The basis, so of course on the two categorical level, it differs. So I started something like 5 minutes late. I will go something like 1 minute over time, so please forgive me. The classification is extremely hard. So in general, that's what I write here on the board. There's not known whether there are finitely many two simples. If you just ask me in private, no, we have a counterexample. But there are details to be checked. So in those cases, actually, it can occur that you have infinitely many two simple representations. Okay. Of course, it doesn't appear on the decategorified level. This is why this is so hard. Let me just state the main theorem, the last ingredient which I promised you. It's my last slide, don't worry. So this H Cell Theorem, because it's very, so this is just the abstract nonsense, but let me just click on this link to make it clearer. So what you can do is, so I already told you we have to only fix on an apex, but it's even better. You only have to fix on the diagonal of an apex. So just take any left cell intersected with its corresponding right cell, L star in my notation, you will find what is called an H cell, which is the diagonal. And it turns out that the representation theory associated to this cell is controlled by what is associated to this small cell. In particular, in this case, for the symmetric group, this will tell you you have a huge cell. God knows how it looks like, but any intersections with zillions of elements, 1 million, God knows, any square number, intersections will always be 1. So the corresponding two representations associated to this cell are in one-to-one correspondence with two representations with a category with one indecomposable object, with one simple object in this case. And I guess it's not very hard to believe that a category with one simple object has not a very complicated two representation theory. It has just one associated simple. And that's exactly the corresponding cell module you see here. Remember that all of those are equivalent. So we have reduced the problem from a huge cell onto the diagonal. This is this very, very nice H cell theorem, which in some sense goes back to Green. I'm out of time, but I could explain why. And this is my last link to click on. We hope that this actually gives, so this was this big cell in type B6. Again, this cell has whatever, how many elements, 50,000 elements. You can reduce to an H cell, which in this case is 4. So we have reduced already the problem from a category which has something like 40,000 indecomposable objects to a category which has 4 indecomposable objects. That's much better. And actually you can check that the associated category in this case is nothing else. I'm lying a little bit here now, but I'm out of time. Nothing else than vect for the Klein 4 group. Right? 4 elements, it's vect for the Klein 4 group. And I've calculated the rank sequence before. And by miracle, those numbers turn up in the corresponding row, as they should. Because that's kind of the contents of the H cell theorem. But notice one thing, that's the last thing I say. 1, 2, 3, 4, 5. So here we have 5 equivalence classes of cell modules, right? They're all different, they have all different numbers. But you have 6 associated simples coming from the Klein 4 group, right? Which means there's a non-cell representation, non-cell true representation in this case, which makes me very happy because this was the first case we found outside of the dihedral type where cell and non-cell differs. This is the first example I found in type B6. Hooray. And afterwards, of course, as soon as you find one example, you find zillions. But this was the first one. The one thing to stress here is you reduce the problem from 50,000 elements to 4. And it doesn't get much worse, for instance, in type E8, you can reduce the problem from a cell with 400 million elements to a cell with 7 elements. Something like this. So the H cell theorem is super powerful. So that's what we hope to prove. So the main theorem we hope to prove, use this H Cell Theorem to reduce it to this case where you see something like with 5 elements, 4 elements, whatever. And just use the classification here to get the classification here. But I'm out of time. Thank you very much.
Questions for Dan?
Sorry, I got confused. In which sense do you get M0 algebras and M0 modules from two categories?
Say it again, it was.
Fill it out. If you have finitely two categories,
You indecomposable objects, you can multiply them, tensor them together. They will decompose positively.
the morphisms in this category are quite.
Yeah, the morphisms you don't see on the D category file level.
I mean, when you say tensor objects, objects in the two category are just objects.
I was talking in the monoidal category. In the 2 category, you tensor one morphism, also you compose one morphisms. In the 2 category, you don't care about the objects, the one morphisms are there.
Okay, so the morphisms correspond to algebras?
To the basis elements.
To the basis elements?
The 2 category of 2 representations of such a finitary 2 category is not a finitary 2 category, but something which seems to be quite close to being finitary 2 category. Is this some kind of generalization of this notion where you say it was a direct sums for objects or something which
No, in general, I don't think so. Those guys are very complicated.
So you have mentioned representations of the taxonomy algebra. And what about this version of categorical SL2 by Elias and Shi? So it's a total community.
Oh,
Any idea?
actually, there are some ideas using some kind of PDG2 representation theory, but it gets super technical, okay? And I'm not the expert to ask. But yes, it's a natural question people consider.